Welcome to the second half of Lecture 4.1. I actually ought to not call this lecture binary ionic compounds, simply because in part 2 we get into polyatomic anions, and so more appropriately we should just scratch that part out. The binary, just kind of, scratch it out, get rid of it, and just call these ionic compounds. So basically, off we go. Covalent bonding in ionic species. Oxoanions. In the case of oxoanions, the central atom is surrounded by a number of covalently bound oxygens. They can number generally from 1 to 4 oxygens around the central atom, which is typically a nonmetal. However, there are a few oxoanions where they have a metal in the center of them, and we will talk about those. The names of oxoanions usually end in ATE or ITE. There are 3 basic patterns among the nonmetal and metalloid oxoanions. The period 2 oxoanions of boron, carbon, and nitrogen as central atoms. The suffix ATE is associated with having 3 oxygens, and the suffix ITE is associated with 2 oxygens. The charge is the group number minus 16, not the group number minus 18, with the pattern of the monatomic anions that we saw previously. And here is what we have. BO3, 3 minus, borate as with the boron as a central atom. CO3, 2 minus, is carbonate. And associated with that is HCO3 minus, hydrogen carbonate, or also called bicarbonate. What has happened in this case is the CO3 2 minus has gained an H plus, or a proton, to become HCO3 1 minus. So the H brings in a positive charge, decreasing the net charge to a -1. It also has a trivial name, bicarbonate. NO3 1 minus is nitrate, and this is the first central atom where we come across the ITE form, and that is NO2 minus is nitrite. And in general, we see that boron and carbon are in groups 13 and 14. So those two groups, 13 and 14, don't have an ITE form in their oxoanions. They are ATE forms only. We'll find that in groups 15 and 16, there is the ATE form and there is an ITE form also. The rules for the group 17 oxoanions. These are oxoanions with chlorine, bromine, and iodine as the central element. We don't include fluorine or astatine at this point. There are basically 4 oxidation states for these. When the central atom is surrounded by 4 oxygens, we have the prefix per and the suffix ate. So, for example, ClO4 minus is perchlorate. And I lost space there. With 3 oxygens, we lose the per, but we still keep the ate and add that to the root name. So we end up with ClO3 minus, and that is chlorate. When we get down to 2 oxygens, the suffix is changed to ITE. So ClO2 with the negative charge is chlorite. And then finally, when we get down to one oxygen with the chlorine, we have to put the prefix hypo in front, and this is hypochlorite. All these oxoanions have a -1 charge, as you would expect in group 17, and this pattern is followed through all three of the central atoms: chlorine, bromine, and iodine. So I've also shown here per bromate, BrO4 minus, and I wrote bromate and I meant to write iodate for IO3 minus. This slide gives a summary of everything that is on the group 17 oxoanions. For the chlorine, the bromine, and the iodine. The remainder of the nonmetal and metalloid oxoanions have 4 oxygens associated with the ATE suffix and 3 oxygens associated with the ITE suffix. This is different from what we had previously studied, wherein 3 oxygens was ATE and 2 oxygens was ITE. But just to remember, again, here we have 4 oxygens for the ATE suffix and 3 oxygens for the ITE suffix. And the charge is the group number -18, which is the same pattern as we found in the monatomic anions. So here are some period 3 oxoanions. SiO4 4- is silicate. Because it is in group 14, we do not find a silicite in the pattern. In group 15, we have phosphate, PO4 3-. We can add hydrogens to it like we did with carbonate. 1 hydrogen added to this is hydrogen phosphate with a 2- charge. We can also add a second hydrogen, H2PO4 -1, and we call that dihydrogen phosphate. Correspondingly are the PO3 3- series. So PO3 3- is phosphite, HPO3 2- is hydrogen phosphite, and H2PO3- is dihydrogen sulfite. Now we move on to the sulfur oxoanions. SO4 2- is sulfate, and HSO4- is hydrogen sulfate, and it has a trivial name of bisulfate. SO3 2- is sulfite, and HSO3 1- is hydrogen sulfite with the trivial name of bisulfite. Finally, we look at some less common oxoanions from periods 4 and 5, and we find that they follow the same pattern we were just using. ASO4 3- is arsenate. 1 oxygen fewer, ASO3 3- is arsenite. SeO4 2- is selenate, and SeO3 2- is selenite. TeO4 2- is tellurate, and TeO3 2- is tellurite. Other polyatomic ions. Polyatomic cations. Hg2 2+ is the mercury 1 diatomic cation. It is 2 mercury 1+ cations held together by a covalent bond. NH4 is the ammonium cation. This also designates an anionic compound along with a metal. So when you're looking to know if your compound is ionic or not, a metal is not the only indicator. The ammonium cation is another indicator that you have an ionic compound. There are several polyatomic anions that end in IDE, like our monatomic ones. First one is Cn-, cyanide. Then OH- is hydroxide. This is the basis for our basic compounds. O2 is peroxide. And it is like the mercury 1 in that two oxygens are bound together covalently, and each one has a -1 charge. Azide is N3-, not to be confused with N3-, which is the monatomic anion of nitrogen, which is nitride. Azide is 3 nitrogens bound together with a negative charge. Then we have 3 polyatomic oxoanions that have metals as their central atom. Chromate is CrO4 2-. Dichromate, Cr2O7 2-. This molecule has 2 centers, and MnO4- is permanganate. Naming is just as we saw with a metal followed by the non-metal, but in this case we can also include the ammonium ion. So we give the name of the cation followed by the name of the anion. So going back to the binary compounds, K2O is potassium oxide. Mg, not Mn, NO3 in parentheses with a 2 is magnesium nitrate. And when there's more than one polyatomic ion needed in the formula, that ion is enclosed in parentheses with the subscript on the outside to designate how many of those ions are present. Number 3 is ammonium hydroxide. This is an ionic compound of the ammonium ion and the hydroxide ions. And then we have a copper compound with SO3. SO3 is sulfite, and it has a 2- charge. And copper is a transition metal needing a Roman numeral designation. So the 2 coppers have to sum up to +2. We're going to divide that by 2 because there are 2 coppers. So each one is +1. So we have Cu+ and Cu+. With the sulfite, so this is copper 1 sulfite. Next we move on to acids. The oxoacids are the acids of the polyatomic anions with enough hydrogens to make it a neutral compound. And their naming is also systematic. Here are a few examples. NO3 is the anion for nitric acid, and the anion is nitrate. In carbonic acid, CO3 has a 2- charge, so it needs 2 hydrogens. Phosphoric acid is the acid of phosphate, and phosphate is PO4, 3-, so it needs 3 hydrogens. And then finally, HClO3 is chloric acid. So let's look at the systematic way that they are named. If we look at the anion, if the anion ends in ATE, as in phosphate, the corresponding acid is the IC acid. H3PO4 is phosphoric acid. For those oxo acids with an polyatomic anion that is an ITE, as in phosphite, PO3, 3-, the corresponding acid ends in OUS, acid. So H3PO3 is phosphorus acid. Finally, I'd like to jump down to the bottom of this table and look at the oxo acids of the halogens. Remember that ClO4- is perchlorate. When we make it an acid, we do not change the per. We leave that, and we end up with perchloric acid. ClO3- is chlorate. Remove the 8, put IC acid. Chloric acid. Chlorite, ClO2-, add a hydrogen and change the ending to OUS acid. Chlorous acid. And then finally, hypochlorite. Again, we keep the prefix hypo and change the ITE to OUS acid. So HClO is hypochlorous acid. Bases. Bases are substances that yield hydroxides when dissolved in water. More commonly, they are hydroxides in and of themselves with a metal ion associated with them, such as sodium hydroxide, potassium hydroxide, or barium hydroxide. However, there are some compounds that when dissolved in water will remove a hydrogen ion from a water molecule, leaving a hydroxide ion as the base. And these are ammonia and amines. Amines are organic molecules that have an nitrogen in it. So ammonia, NH3, when put in water, becomes ammonium hydroxide, which is a base. And methylamine, when put in water, also pulls a hydrogen off a water molecule and produces hydroxide. We call that methylammonium hydroxide. And then lastly, in this example, is an ethyl group attached to the NH2, and that's called ethylamine, and it too, like the methylamine, produces hydroxide. And last are the hydrates. These compounds have a specific number of water molecules within the solid structure, and the formula has 2 parts. The first part is the ionic compound without the water, or in other words, anhydrous, followed by a dot, then the number of water molecules associated with each formula unit of the salt. And a Greek prefix is used to tell you how many water molecules are present. For example, CuSO4.5H2O is copper 2 sulfate pentahydrate. The anhydrous compound would just simply be copper 2 sulfate. And down here in the picture is a picture of the 2 different ones. This is the pentahydrate, the blue substance, and the white substance here is the anhydrous form.